Picture a sky not with one sun, but two, casting long, ever-shifting shadows across a landscape of crystalline forests. Imagine a world where the clouds aren't made of water, but of scorching sand, and the rain that falls is molten glass, sideways, in hurricane-force winds. This isn't a scene from the latest science fiction blockbuster. These are real, documented environments on planets light years from our own familiar solar system. For centuries, we looked up at the stars and wondered if other worlds existed, picturing versions of our own Earth. But the reality that modern astronomy has uncovered is so much stranger, so much more fantastical than anything we could have dreamed up. The universe is not just a collection of similar rocky orbs. It is a gallery of the bizarre, a cosmic menagerie filled with worlds that defy logic and challenge our very understanding of what a planet can be. This video is your ticket to that gallery. We are about to embark on a journey to the farthest reaches of observable space to uncover 25 of the most peculiar, mind-bending planets ever discovered. These aren't just distant points of light. They are entire worlds with physics and landscapes that seem pulled from the realm of pure imagination. We will visit a planet so dark it absorbs almost all light that touches it, a world where a year lasts only a handful of hours, and another that orbits a stellar corpse, a haunting remnant of a long-dead star. Each of these discoveries rewrites the textbooks and expands our perception of the possible, reminding us that the universe holds wonders beyond our wildest fantasies. So get comfortable and prepare to have your mind expanded. We're about to dive into the cosmic unknown and explore the sheer, breathtaking oddity of these 25 strange planets, a journey that promises to leave you in a state of awe at the magnificent and wonderfully weird universe we are so lucky to call home. First on our journey into the bizarre is a world that makes the fiercest hurricanes on Earth feel like a gentle breeze. Welcome to HD 189,733b, a planet where the very idea of weather takes on a terrifying new meaning. At first glance, this world appears as a beautiful, deep cobalt blue, a serene-looking jewel hanging in the blackness of space. But this tranquil color is a cosmic lie, the calm before an eternal storm of unimaginable ferocity. This azure hue doesn't come from peaceful oceans, but from a hazy, choking atmosphere filled with silicate particles, the very same material that makes up glass here on Earth. This is a gas giant, meaning it has no solid surface to stand on. But if you could find a way to float in its upper atmosphere, you would experience a true hellscape. The winds here don't howl, they scream across the planet at a staggering speed of 5,400 miles per hour. To put that in perspective, that's over 7 times the speed of sound. These supersonic gales would instantly shred any known material to dust, whipping around the planet in a relentless global tempest. The horror doesn't stop with the wind. The temperature on its day side, the side permanently facing its host star, soars to a blistering 1,700 degrees Fahrenheit. At such extreme heat, those silicate particles in the atmosphere don't just float, they melt. And what falls from the sky isn't water, but a torrent of superheated, molten glass. Because of those incredible winds, this glass doesn't fall down. It rains sideways, scouring the atmosphere in a horizontal, scalding barrage. Scientists determined these terrifying conditions by observing the planet as it passed in front of and then behind its star. By analyzing the specific colors of light absorbed and emitted by the planet's atmosphere, a technique known as spectroscopy, they were able to detect the signature of silicate vapor. This close orbit is the engine of this chaos. The planet is locked in an incredibly tight embrace with its star, completing a full orbit in just 2.2 Earth days. This proximity creates an extreme temperature difference between the scorching day side and the slightly cooler night side. And it's this differential that fuels those perpetual supersonic winds, creating a world that is both breathtakingly beautiful and utterly hostile to life as we know it. From a world of unimaginable storms, we travel to a planet of almost incalculable value, a place where the phrase, "a diamond in the sky," is not a metaphor but a literal scientific description. Meet 55 Cancri, a super-Earth that has captured the public imagination like few other exoplanets, earning it the dazzling nickname, the Diamond Planet. Located a relatively close 41 light-years away in the constellation Cancer, this world orbits a sun-like star, part of a binary system, and it is anything but Earth-like. While it's classified as a super-Earth because its radius is about twice that of our own planet, and its mass is over 8 times greater, the similarities end there. This is a world of extremes, a crucible of heat and pressure that has forged something truly extraordinary. The key to understanding this world's incredible nature lies in its composition. Astronomers determined that 55 Cancri must be composed largely of carbon, based on measurements of its mass and radius, which together reveal its density. The numbers pointed to a planet far too dense to be a gas giant, yet with a chemical makeup utterly different from our own rocky, oxygen and silicon-rich Earth. The prevailing theory is that under the immense pressures found deep within this planet, pressures that could be millions of times greater than what we experience at sea level on Earth, carbon atoms are forced into a rigid crystalline structure. That structure is what we know on Earth as diamond. In essence, a significant portion of this planet's interior is likely a solid mass of diamond, potentially up to a third of the entire world's composition. If you could somehow mine this celestial jewel, its value would be beyond any earthly economy, but the reality of visiting it is a different story altogether. This diamond doesn't sit in a tranquil, cool setting. The planet orbits its host star with such incredible speed that a single year, one complete trip around the star, takes less than 18 hours. This proximity means the planet is tidally locked, with one hemisphere permanently facing the star, creating a surface temperature on that day side that soars to a searing 4,400 degrees Fahrenheit. That's hot enough to melt most metals and certainly far too hot for any diamond to remain pristine on the surface. On the day side, the very surface rock may be a bubbling ocean of molten lava. The night side, while cooler, is still an inferno. Recent studies have even suggested that the planet's atmosphere might be rich in carbon, potentially spewing hydrocarbons into the space around it. So, while the idea of a glittering, Earth-sized diamond is a captivating one, the true nature of 55 Cancri is even more complex and hostile. A carbon-rich world forged in a stellar furnace, its heart a priceless gem of almost planetary proportions, forever locked in a blistering, tight orbit around its sun. Moving from a world forged in fire and carbon, we encounter a celestial marvel that puts our own solar system's most iconic feature to shame. If you think Saturn's rings are impressive, prepare to have your expectations completely rewritten by the staggering spectacle of J1407b. Often called the Super Saturn, this distant object, which may be a giant gas planet or a small, failed star known as a brown dwarf, is home to a ring system so colossal that it makes Saturn's beautiful bands look like a child's toy. Discovered not by directly imaging its faint light, but by watching the subtle, complex way it dimmed its parent star, this object revealed a secret that stunned astronomers. The story of its discovery is a masterpiece of indirect observation. As J1407b passed in front of its star from our vantage point, an event known as a transit, it didn't cause a simple, brief dip in starlight. Instead, the star's light flickered and faded in an incredibly intricate and prolonged dance, a pattern of dimming that lasted for 56 days. This wasn't the signature of a single, solid object blocking the light, but of a vast, complex structure of rings with gaps and divisions, eclipsing the star in a series of complex steps. When astronomers decoded this incredible light curve, the scale of the discovery was almost incomprehensible. the ring system surrounding J1407b is believed to be nearly 200 times larger than Saturn's. To put that in perspective, if you could place this ring system in our own solar system where Saturn resides, it would dominate our night sky. The rings would appear larger than several full moons, a breathtaking, luminous arc stretching across the heavens. The entire structure is an estimated 70 million miles in diameter, a disk of dust, rock, and ice so vast it could contain the orbits of all the inner planets of our solar system with room to spare. This isn't just a single, solid band. It's a complex system of at least 37 distinct rings, each one a highway of countless orbiting particles. But perhaps the most tantalizing clue hidden within this data is the presence of sharp, clean gaps between some of the rings. On Saturn, gaps in the rings are often cleared out by the gravitational influence of small shepherd moons. The clear, defined gaps in J1407b's rings strongly suggest that exomoons moons orbiting a planet outside our solar system are in the process of formation there right now. The gravitational pull of these infant moons is likely sculpting the ring material, sweeping their orbits clean and creating those dark divisions in the vast, bright disk. This makes the system a real-time laboratory, a snapshot of a moon-forming factory that mirrors the processes we believe formed the many moons of our own gas giants billions of years ago. While we cannot see this magnificent structure directly, its shadow play against a distant star has given us a glimpse of one of the most magnificent and dynamically active systems ever discovered. A place where the birth of new worlds is written in the dark spaces between rings of cosmic dust. Leaving behind the magnificent rings of Super Saturn, we arrive at a world that seems to defy the most fundamental laws of physics. Gliese 436b presents us with a cosmic paradox that sounds like something from a wizard's tale, a planet covered in burning ice. Imagine a world where the temperature is a constant, blistering 822 degrees Fahrenheit, hot enough to melt lead and turn rock into lava. Under any normal circumstances, you would expect all water to have long since boiled away into space as superheated steam. And yet, Gliese 436b, a Neptune-sized planet orbiting perilously close to its red dwarf star, is cloaked in a thick layer of solid water. This isn't a mistake in observation. It's a breathtaking demonstration of how extreme conditions can create materials with properties that seem impossible in our everyday experience. The secret to this mysterious hot ice lies in the immense power of gravity and pressure. While the surface temperature is scorching, the planet's powerful gravitational field, a result of its significant mass, creates an astonishingly dense and heavy atmosphere. This atmosphere acts like a colossal, invisible weight, pressing down on the planet's interior with a force thousands of times greater than the atmospheric pressure on Earth. Under this incredible compression, the water molecules on Gliese 436b are not allowed the freedom to bounce around as a gas, no matter how much thermal energy they have. Instead, they are literally crushed together, forced into a highly ordered, compact crystalline structure. This is the very definition of a solid, but one that exists at a temperature where it should be a vapor. Scientists refer to this exotic state of matter as Ice 7, or superionic ice, a form of water ice that is both solid and incredibly hot, its molecules locked in a rigid lattice by pressure alone. Think of it like a diamond being formed deep within the Earth. Carbon, under normal surface conditions, is soft graphite. But when subjected to the extreme heat and pressure of the planet's mantle, its atomic structure rearranges into the hardest known natural material. Gliese 436b is doing the same thing with water. The star's heat provides the energy, and the planet's own gravity provides the anvil, forging a shell of ice that stubbornly remains solid in the face of an inferno. This creates a truly alien landscape. The planet's surface might feature vast, steaming plains of this hot ice, perhaps glowing with a dull red heat from the nearby star. It could be sculpted into towering, pressurized ice mountains that are simultaneously on fire, their bases constantly melting and re-solidifying under the intense atmospheric squeeze. This world is a perfect laboratory for studying states of matter that we can only create for fleeting moments in high-pressure physics experiments on Earth. Its very existence proves that the universe operates on a set of rules far more flexible and wondrous than we once imagined, where ice doesn't need cold and fire can't always melt what it touches. Now, let us turn our gaze to a world of perfect darkness, a place where light goes to die. In the constellation Draco, orbiting a star some 750 light-years away, is a gas giant known as TRES-2b, officially the darkest planet ever discovered in our galaxy. This world is an enigma, a pitch-black orb that reflects less than 1% of the light that strikes its atmosphere. To put that staggering statistic into perspective, coal, one of the blackest common substances on Earth, reflects about 10% of incoming light. Acrylic black paint reflects around 5%. TRES-2b is blacker than both, a void in space so profoundly dark that if you could magically float alongside it, you would struggle to perceive its shape against the deeper black of the cosmos. It is less of a celestial body and more of a shadow, a ghost planet that absorbs nearly every single photon that dares to touch it. Scientists first uncovered its profound darkness using a Kepler space telescope, which was designed to hunt for planets by detecting the tiny dips in a star's brightness as a world transits or passes in front of it. When TRES-2b crosses the face of its yellow, sun-like star, the star's light dims by an almost imperceptible amount. But crucially, the telescope also measured the light from the system when the planet passed behind the star, a moment known as secondary eclipse. This is when the planet's own faint glow, or its reflected starlight, is temporarily blocked from our view. For most hot Jupiters, this creates a small but measurable change in the total light, as these worlds are often bright and reflective. For TRES-2b, however, the drop in light was vanishingly small. The planet was contributing almost no reflected light to the system at all. The data revealed a geometric albedo, the measure of a body's reflectivity, of less than 1%, confirming its status as a cosmic abyss. So what could possibly create an atmosphere this voraciously dark? The leading theories point to a truly alien atmospheric chemistry, a hellish brew utterly unlike anything in our solar system. The planet is a searing hot Jupiter, orbiting its star at a distance of only 3 million miles, which leads to a dayside temperature of around 1,800 degrees Fahrenheit. At these extreme temperatures, the atmosphere is likely filled with vaporized sodium and potassium, along with gaseous titanium oxide. But unlike the reflective clouds we see on Jupiter, which are made of ammonia and water ice, the clouds on TRES-2b may be absent altogether. The intense heat might prevent any reflective, high-altitude clouds from forming, leaving the starlight to penetrate deep into an atmospheric soup of light-absorbing chemicals. Some researchers propose that the atmosphere is rich in a particular form of vaporized sodium that absorbs light in the red part of the spectrum exceptionally well, or that gaseous titanium oxide is a powerful light absorber. Yet, even these exotic substances don't fully explain the profound and total blackness. It's possible the atmosphere contains chemicals we haven't even yet identified, compounds that thrive only in such infernal conditions and possess an almost perfect ability to capture light and convert it into heat. The planet glows faintly, not with reflected light, but with an eerie, deep red ember-like radiance from its own immense thermal energy, a dull blush against an otherwise perfect black canvas. TRES-2b stands as a humbling reminder that for all we have learned, the universe still holds profound and simple mysteries like a planet the size of Jupiter that somehow, defying all expectation, has learned to hide in the darkness. If you think sideways glass rain was extreme, prepare for a world where the very elements of industry and civilization fall from the sky in a torrential, metallic downpour. Our next destination is WASP-76b, a planet that takes the concept of extreme weather and elevates it to a truly mythological scale. This is an ultra-hot Jupiter, a class of gas giants that orbit so close to their stars that their atmospheres are literally boiling away. But WASP-76b has a particularly brutal and unique claim to fame. It is the planet where it rains molten iron. The conditions that create this phenomenal metallic rain are a direct consequence of the planet's tortured relationship with its star. Like many planets in such scorchingly tight orbits, WASP-76b is tidally locked. One hemisphere, the day side, is in a state of permanent, blazing daylight, perpetually facing its host star and subjected to an unending barrage of stellar radiation. The temperature on this side of the planet is a staggering 4,400 degrees Fahrenheit, which is hot enough to not only melt iron but to completely vaporize it, breaking the metallic bonds that hold it together and turning it into a gaseous vapor that mixes with the other atmospheric components. This is where the planet's own atmosphere becomes the engine for its bizarre weather cycle. The incredible, searing heat on the day side creates a massive and constant updraft, with the superheated air and vaporized metals rising high into the atmosphere. Meanwhile, the night side, forever shrouded in darkness, is comparatively cooler, though cool is a relative term, with temperatures still hovering around a furnace like 2,700 degrees Fahrenheit. This dramatic temperature difference, a contrast of thousands of degrees between day and night, fuels supersonic winds that scream across the Terminator line, the boundary that separates eternal day from eternal night. These winds act as a global conveyor belt, transporting the scorching, metal-rich atmosphere from the day side over to the night side. As this atmospheric parcel crosses into the cooler, dark hemisphere, the temperature plummets rapidly. The vaporized iron, no longer energized enough to remain a gas, begins to condense. It forms into droplets, much like water vapor condensing into clouds and rain on Earth. But here the droplets are not made of water, they are globules of liquid molten iron. And so, on the night side of WASP-76b, the skies open up and it rains. It doesn't rain water, it rains a blazing, incandescent shower of liquid metal. The evidence for this incredible phenomenon was gathered by astronomers using the espresso spectrograph on the Very Large Telescope in Chile. They didn't take a picture of the iron rain. Instead, they detected its chemical signature in the planet's light. As WASP-76b transited its star, the instrument was able to analyze the starlight filtering through the planet's atmosphere at the boundary between day and night. On the evening terminator, the line of sunset, they detected a strong and clear signature of iron vapor. But when they looked at the morning terminator, the line of sunrise, that iron signature was mysteriously absent. The most logical explanation is that on the night side, the iron had condensed out of the atmosphere and fallen as rain, leaving the air on that side of the planet largely depleted of iron vapor. It is a stunning piece of detective work that paints a vivid picture of a world with a truly alien hydrological cycle, where the roles of water and iron are swapped in a terrifyingly beautiful planetary scale smelting process. This world is a constant, violent storm of creation and destruction, where elements are vaporized on one side and forged into falling metal on the other, a never-ending tempest written in the language of astronomy and chemistry. From worlds of iron rain and scorching ice, we venture next to a place that for decades existed only in the realm of science fiction. Welcome to Kepler 16b, the first confirmed planet ever discovered orbiting a pair of stars, a real-world Tatooine straight out of the Star Wars universe. Before this discovery, the iconic image of a double sunset on Luke Skywalker's home world was a fantastical concept, a beautiful piece of cinematic imagination. But in 2011, data from NASA Kepler Space Telescope turned that fiction into scientific fact, proving that such worlds not only could exist but actually do in abundance throughout our galaxy. This Saturn-sized gas giant, located about 200 light-years away in the constellation Cygnus, doesn't orbit a single star like our Sun. Instead, it dances in a graceful, wide circle around two smaller, cooler stars that are locked in their own intimate cosmic ballet. The two stars at the heart of this system are a fascinating pair. The larger of the two is a K-type dwarf star, about 69% the mass of our Sun, glowing with a distinct orange hue. Its companion is an even smaller M-type red dwarf, weighing in at just 20% of our Sun's mass. These two stars orbit each other incredibly closely, completing a full loop around their common center of gravity in a mere 41 days. From the perspective of Kepler 16b, these stars would appear as a spectacular double act in the sky. Some days they would be close together, looking like two brilliant, mismatched eyes watching over the planet. On other days, as they moved through their orbit, they would separate, casting complex, ever-changing shadows across the cloud tops of the gas giant. A sunrise or sunset on this world would frequently be a double feature, with two distinct orbs dipping below or rising above the horizon, painting the sky in a symphony of light and color that would make our single sun experiences feel remarkably simple by comparison. The discovery itself was a monumental achievement in the field of exoplanet science, demonstrating the incredible power of the transit method. The Kepler telescope was designed to stare unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars, searching for the telltale, periodic dimming that occurs when a planet passes in front of its host star. The light curve from the Kepler 16 system, however, was unlike any seen before. The starlight didn't dip in a simple, predictable pattern. Instead, it displayed a complex series of eclipses and transits. First, one star would pass in front of the other, causing a deep primary eclipse. Then, the other star would eclipse its partner, causing a secondary dip. And then, crucially, there was a third, much smaller dip in brightness that occurred at times when neither star was eclipsing the other. This third dip could only be explained by the presence of a third body, a planet transiting across first one star and then, at a different point in its orbit, across the other. It was this triple transit signature that provided the undeniable proof of a planet orbiting both stars, a configuration known as a circumbinary planet. The significance of this discovery cannot be overstated. For science fiction, it validated one of its most enduring and beloved images, showing that the universe truly is as strange and wonderful as our stories imagine it to be. For astronomy, it shattered old assumptions. Many scientists had theorized that the chaotic and shifting gravitational forces in a binary star system would make it extremely difficult for planets to form, as the swirling protoplanetary disk of dust and gas would be constantly disturbed. The existence of Kepler 16b proved that planet formation is a far more robust and versatile process than we thought. Planets can and do coalesce in these dynamic environments, opening up a vast new category of potential worlds to search for. While Kepler 16b itself, a cold gas giant with an orbit similar to Venus's, is unlikely to harbor life as we know it, its discovery implies that smaller, rocky planets could also exist in the habitable zones of binary stars. This dramatically increases the number of possible places in the galaxy where life could potentially take root, each one offering a sky with two suns, a permanent reminder of the dynamic and diverse architecture of planetary systems. While the idea of a diamond world or a planet with twin suns captures the imagination, our next destination confronts us with a more primordial vision of planetary hell. Journey with us to Kepler 10b, a world that represents a brutal class of exoplanet known as lava planets. This is not a gas giant cloaked in strange clouds or a world of exotic chemistry, but a scorched, rocky sphere that might show us what Earth looked like in its most violent infancy. Discovered by NASA's Kepler Space Telescope in 2011, Kepler 10b holds the distinction of being the first unequivocally rocky planet ever identified outside our solar system. Before this confirmation, astronomers knew of many giant gassy worlds, but finding a small, dense terrestrial planet was the key milestone in the quest for worlds analogous to our own. The Kepler mission achieved this by detecting the faint, periodic dimming of its host star, a telltale signature of an orbiting body. The data was so precise that scientists could not only confirm the planet's existence, but also calculate its size and mass with remarkable accuracy, revealing a world about 1.4 times the width of Earth and nearly 4.6 times its mass. That incredible density points to a composition of iron and rock, much like Mercury or Earth, but the similarities end there. Kepler 10b orbits its Sun-like star with a ferocious proximity, completing a full year in just 20 hours. To put that astonishing speed into perspective, this planet is more than 20 times closer to its star than Mercury is to our Sun. This intimate dance places it well within what astronomers call the roasting zone, where the stellar radiation is so intense that any solid surface is perpetually baked into a liquid state. The dayside temperature on Kepler 10b is estimated to soar above 2,500 degrees Fahrenheit, a heat so profound it is well beyond the melting point of most common rocky minerals. The surface, therefore, is not a solid landscape of mountains and craters, but most likely a global, raging ocean of molten lava, hundreds of miles deep, shimmering with the horrifying brilliance of a freshly forged world. Imagine the vista from orbit. The star would dominate almost the entire sky, a colossal, simmering disk of fire. Below, the planetary surface would not have distinct features like continents, but would instead be a rolling, seething cauldron of incandescent rock, glowing in shades of brilliant orange and white-hot yellow. There would be no atmosphere to speak of. The star's relentless blasting and the planet's own comparatively weak gravity would have long since stripped away any protective gases, leaving the molten surface exposed directly to the vacuum of space. This means the surface would be in a constant state of violent activity. Without an atmosphere to distribute heat, the side facing the star is an unimaginable inferno, while the perpetual night side would be chillingly cold, though still likely heated from below by the planet's molten interior. This extreme temperature difference could drive supersonic winds in a thin, transient exosphere, scouring the surface and perhaps creating monstrous lava tides, pulled by the star's immense gravity that would slosh across the entire planet in slow, glowing waves. The discovery of Kepler 10b was a landmark because it proved that small, rocky worlds can exist in environments of extreme punishment, pushing the very definition of a terrestrial planet to its limits. It serves as a stark reminder that the galaxy is filled with a vast spectrum of worlds, from the potentially habitable to the utterly inimical, and that our own placid Earth represents just one possible, and perhaps rare, outcome in the chaotic process of planetary formation. But beyond the blistering heat of lava worlds lies a system of an entirely different and far more sinister nature. Imagine a star that has already died a violent death, yet its gravitational influence still commands a family of orbiting worlds. This is the reality of the PSRB 1257+12 system, home to the first exoplanets ever confirmed around a Sun-like star, yet they circle a stellar corpse known as a pulsar. These are not worlds bathed in the nurturing light of a stable sun. They are zombie planets orbiting the ghost of their former star in a permanent high-energy graveyard. A pulsar is the incredibly dense, rapidly spinning core of a massive star that has gone supernova. When such a star exhausts its nuclear fuel, its own immense gravity causes it to collapse in on itself and then explode outward in one of the most energetic events in the universe. What remains is a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. If this neutron star is spinning and emits beams of radiation from its magnetic poles like a cosmic lighthouse, we call it a pulsar. The pulsar at the heart of this system, discovered by the Arecibo Observatory in the early 1990s, spins at a dizzying rate of over 160 times per second, sending out a precisely timed pulse of radiation with every rotation. The existence of planets here was a profound mystery. The supernova explosion that created the pulsar would have been catastrophic, releasing more energy in a few moments than our Sun will over its entire 10 billion-year lifetime. Any planets that orbited the original star would almost certainly have been utterly vaporized or flung out into the interstellar void. So how did these zombie worlds come to be? Astronomers have developed two compelling and equally dramatic theories. The first is a story of cosmic survival against all odds. It is possible that these are the scorched, rocky cores of former gas giants, worlds that somehow managed to cling to existence while their outer gaseous layers were violently stripped away by the supernova blast. They would be the sole charred survivors of a complete planetary system annihilation. The second, and perhaps more likely, theory is a story of rebirth from destruction. The Titanic explosion would have created an immense cloud of debris, a mixture of material from the star itself and the shredded remains of any original planets. In the aftermath, this debris could have coalesced anew, forming a second generation of planets from the ashes of the first. These would not be the planets that lived through the death of their star, but rather planets born from that very death. The environment these planets endure is unlike any other we have encountered. They are bathed not in warm, visible light, but in a relentless, deadly hail of high-energy radiation from the pulsar. This includes X-rays and gamma rays, forms of energy so powerful they would instantly sterilize any known form of life and strip away any substantial atmosphere a planet might try to hold onto. The three known planets in this system are all closer to their pulsar than Mercury is to our Sun, completing their orbits in periods of days. They are likely barren, airless rocks, their surfaces constantly bombarded by this invisible, lethal rain. If you could stand on one of these worlds, the sky would not be blue or black, but would likely shimmer with an ethereal, terrifying light. The glow of intense auroras created as the pulsar's radiation interacts with the planet's surface and any thin, transient atmosphere. The pulsar itself would not be a bright disk, but a tiny, piercing point of light, blinking on and off with metronomic precision, a constant, rhythmic reminder of the dead star that rules this system. The discovery of these zombie worlds was a landmark that proved planets are far more tenacious and versatile than we ever imagined. They can form in the most hostile of environments, from the debris of stellar catastrophe, forever orbiting the eerie, rhythmic beacon of their deceased creator. While the binary suns of Kepler 16b feel like a fantastical step up from our own solar system, the universe has an even more spectacular celestial arrangement in store. Prepare to have your conception of a star system completely redefined by HD 188,753 AB, a gas giant that doesn't just orbit two stars, but exists within the mind-bending gravitational embrace of three. In the constellation Cygnus, about 150 light-years away, this planet performs a complex cosmic ballet in a system that is more hierarchical family than a simple pair. For decades, many astronomers doubted that planets could form in such dynamically chaotic multi-star environments, believing the competing gravitational pulls would tear apart the protoplanetary disk of dust and gas needed for planet formation. The very existence of HD 188,753 AB, therefore, was a revolutionary discovery that challenged our fundamental models of how planetary systems come to be. To understand this world, you first have to understand the intricate dance of its three suns. The system is organized like a nested set of Russian dolls. At the very center is a close-knit binary pair. A yellow star similar to our Sun and a smaller orange star orbit each other incredibly tightly, completing a full circle in just 25.5 days. From a distance, this dynamic duo would appear as a single, brilliant point of light, but they are not alone. circling this central pair at a distance roughly equivalent to Saturn's orbit in our solar system, is a third star, a red dwarf. This outer star takes many years to complete a single, stately orbit around the inner binary, and it is within this gravitational framework that the planet HD 188,753 AB exists. The gas giant orbits only the central yellow star, whipping around it in a scorchingly fast orbit of just 3.35 days. This means the planet is perpetually inside the stellar traffic circle, looking out at its complex family of suns. From the cloud tops of this Jupiter-like world, the sky would be a spectacle beyond any science fiction. The dominant feature would be the large, brilliant yellow primary sun, the planet's direct parent star. But very close to it in the sky, you would see its constant companion, the smaller, orange star, a persistent and vivid partner. Depending on their orbital positions, these two might sometimes appear to merge into a single, elongated egg of light, or they could be clearly separated, casting double, shifting shadows across the planet's atmospheric bands. And then, farther out, the third star, the red dwarf, would hang in the sky like a glowing ember, a permanent, deep red jewel that never rises or sets in the same way our sun does, but instead slowly drifts through the constellations over the course of its long orbital period. The colors in the sky would be a constant, breathtaking mix, the harsh white-yellow of the primary, the softer amber of the close binary, and the dim, ruddy glow of the distant red sun, creating a permanent, surreal twilight filled with conflicting hues and an ever-changing play of light and shadow. A single sunset could involve one, two, or even all three of these stars dipping below the horizon in a slow, majestic sequence. The discovery of this planet was a triumph of astronomical technique and persistence. It was detected using the radial velocity method, which involves looking for the subtle wobble in a star's light caused by the gravitational tug of an orbiting planet. But in a triple star system, this is like trying to hear a single, quiet whisper in a room full of people having three separate, loud conversations. The gravitational influences of all three stars create a complex background signal that must be meticulously modeled and subtracted before the tiny signature of a planet can be revealed. The fact that astronomers were able to tease out this signal proved that planet formation is an incredibly robust process. It suggests that protoplanetary disks can be stable enough to coalesce into gas giants even in the gravitationally stirred-up environment near a close binary pair. HD 188,753 AB is not a placid world. It is a testament to chaos and order coexisting, a giant planet that formed in a celestial environment we once thought was too volatile for such delicate construction. It stands as a beacon of the galaxy's diversity, proving that wherever there is a star, or even three, there is likely a way for planets to find a home. From a system haunted by a stellar ghost, we plunge directly into the heart of a different kind of inferno. Meet Co-Rho T7b, a world that doesn't just flirt with extreme heat, it embraces it with a terrifying, all-consuming passion. Discovered in 2009 by the European Space Agency's Co-Rho T satellite, this planet earned a monumental title in the annals of astronomy, the first confirmed rocky exoplanet ever found outside our solar system. Before this moment, we knew of many gas giants and a handful of mysterious intermediate worlds, but Co-Rho T7b provided the long-sought proof that other star systems could forge small, dense terrestrial planets just like Mercury, Venus, and Earth. This confirmation was a watershed moment, opening the door to the search for truly Earth-like worlds and forever changing our perspective on the cosmos. But the planet's true nature is far from a comforting mirror of our own home. It is a vision of primordial chaos, a place where the very rock itself is forced to behave in ways we would only expect from water or air. This scorched world orbits a sun-like star located about 500 light-years away in the constellation Monoceros, the Unicorn. Its orbit is almost inconceivably tight, a mere 1.7 million miles from its stellar furnace. To grasp that distance, consider that Mercury, the innermost planet of our own system, orbits at an average of 36 million miles from the Sun. CoRoT T7b is 20 times closer, completing a full journey around its star in a blistering 20 hours. This means a single year on this world passes in less than one Earth day. Such intimate proximity has a dramatic consequence. The planet is almost certainly tidally locked, with one hemisphere permanently facing the star in a blazing, unwavering glare, and the other trapped in permanent, frigid night. The temperature difference between these two sides is one of the most extreme in the known universe. On the day side, surface temperatures are calculated to reach a searing 4,000 degrees Fahrenheit. This is far hotter than the melting point of most common rocky minerals like basalt and granite. As a result, the entire sun-facing hemisphere is not a solid landscape but a global, roiling ocean of molten lava, thought to be hundreds if not thousands of miles deep. This is not a placid sea. The immense gravity of the nearby star would pull on this liquid rock, creating colossal lava tides that would slosh across the planet in slow, incandescent waves, constantly reshaping its fluid surface. If you could shield your eyes from the stellar glare, you would see a horizon of glowing, orange-white liquid rock, shimmering with heat and violence under a star that dominates the sky. The atmosphere, or what passes for one, is just as alien. The incredible heat on the day side is sufficient to do more than just melt rock. It actually causes the surface minerals to sublimate, to turn directly from a solid or liquid into a gas, bypassing the liquid state entirely. This means the air on CoRoT T7b is likely a thin, tenuous haze of vaporized rock. Picture a mist composed of silicate and metallic vapors rising from the lava ocean like a deadly, shimmering fog. This rock vapor would then be carried by high-altitude winds toward the frigid night side. As this gaseous rock crosses the terminator into darkness, the temperature plummets by thousands of degrees, causing the mineral vapors to condense and solidify. The result, it doesn't rain water on CoRoT T7b. It rains pebbles and tiny stones. A constant, slow hail of solidified rock would fall from the sky on the night side, perhaps collecting in vast, dark plains of gravel and dust, only to be slowly recycled back into the dayside lava ocean over geological time. This creates a complete, if horrifying, geological cycle where rock is vaporized on one side of the planet and condenses back into solid form on the other. The significance of CoRoT T7b's discovery extends far beyond its own nightmarish conditions. It proved that the techniques for finding small, rocky worlds were viable, paving the way for missions like Kepler and TESS to find thousands more. It provided the first direct evidence that the basic ingredients for terrestrial planets' iron cores and rocky mantles are common throughout the galaxy. But perhaps most importantly, it showed us a stark and brutal vision of a rocky planet's possible fate. CoRoT T7b may be what remains of a much larger gas giant, a world that migrated too close to its star and had its vast, gaseous envelope completely boiled away by the intense radiation, leaving behind only its naked, rocky core to endure the hellish conditions. This world is a cautionary tale written in fire and stone, a demonstration of the fine line between a habitable world and a scorched cinder, and a humbling reminder that the universe is capable of forging beauty and terror in equal, spectacular measure. Shifting our focus from worlds of fire and molten rock, we now embark on a journey to the opposite end of the thermal spectrum, arriving in the deep, silent freeze of the galactic outskirts. Here we find Ogle 2005b G390lb, a world so profoundly cold it makes the ice caps of Mars feel balmy by comparison. Nicknamed the frozen super-Earth, this planet is a testament to the fact that extreme environments are not limited to scorching orbits. They also exist in the dark, frozen wastes far from a star's warming embrace. Located an immense 21,000 light-years away, near the center of our Milky Way galaxy, this world orbits a dim, low-mass red dwarf star. Its surface temperature is estimated to be a staggering 364 degrees Fahrenheit below zero, a chill so deep that it is only about 50 degrees above absolute zero, the theoretical point where all molecular motion ceases. On this planet, the very air we breathe would freeze solid in an instant, falling to the ground as a blanket of nitrogen and oxygen snow. The discovery of this icy realm was a monumental achievement in astronomical ingenuity because it was found using a method completely different from the transit or radial velocity techniques we've discussed so far. Ogle 2005 BLG 390 LB was detected through a phenomenon known as gravitational microlensing. This process relies on the gravity of a foreground star acting as a natural magnifying glass. When a star passes almost directly in front of a more distant background star from our viewpoint on Earth, the gravity of the foreground star bends and amplifies the light from the background star, causing it to temporarily brighten. If the foreground star has a planet orbiting it, the planet's own gravity can create a secondary, much smaller spike in the brightness of this cosmic lensing event. This is an incredibly rare and delicate alignment. It requires a perfect lineup of observer, lens star, and background source star across thousands of light years. The Optical Gravitational Lensing Experiment, or OGLE, which discovered this planet, constantly monitors millions of stars in dense stellar fields toward the galactic bulge, waiting for these fleeting brightening events. The signature of the planet was a tiny blip lasting only a day, a whisper of data hidden within the light curve that announced the presence of a small, cold world. This method is uniquely powerful for finding planets that are very far away, very cold, or orbit at great distances from their host stars' worlds that are essentially invisible to other detection techniques. So, what would it be like to stand on this frozen super-Earth? The landscape would be one of profound stillness and darkness. The parent star, a faint red ember in the sky, would provide little more light than a full moon does on Earth, casting weak, deep crimson shadows across the terrain. The surface itself would be a rugged rock and ice world. With a mass about 5.5 times that of Earth, the gravity would be noticeably stronger, making every movement a laborious effort. The ground beneath your feet would not be water ice, which would be as hard as steel at these temperatures, but likely a frozen slab of solid nitrogen, oxygen, and argon, the primary components of what would have been an atmosphere on a warmer world. Here, these gases are permanently frozen into a thick glacial crust. There might be towering mountains of this exotic ice and vast, flat plains that have remained untouched for billions of years. The planet is so cold that any geothermal heat from its core would be utterly insignificant against the relentless chill of space, leaving the surface a frozen, fossilized record of its ancient past. The discovery of this world dramatically expanded the known territory where planets can exist, proving that they can form and persist in the cold, sparse regions of star systems, far from the traditional habitable zone. It is a lonely sentinel in the galactic dark, a frozen time capsule that challenges our Earth-centric search for life while simultaneously showcasing the incredible versatility and reach of modern astronomical discovery. After exploring the frozen wastes of distant super-Earths and the scorching hellscapes of lava worlds, our journey now brings us to a place that feels, for the first time, strangely familiar. We arrive at Kepler 186f, a world that made headlines across the globe as a monumental milestone in the search for life beyond Earth. This wasn't just another exoplanet discovery. It was the first time we had ever found a world almost exactly the size of our own, nestled comfortably within the habitable zone of its star. The habitable zone, often poetically called the Goldilocks zone, is that narrow, precious orbital region where the temperature is just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. And since everywhere we find liquid water on Earth, we find life. The discovery of Kepler 186f was a powerful sign that planets with the fundamental ingredients for life might not be rare oddities but common features throughout the cosmos. Located about 500 light-years away in the constellation Cygnus, Kepler 186f orbits a star quite different from our Sun. It's a red dwarf, also known as an M-dwarf, which is the most common type of star in our galaxy. These stars are smaller, cooler, and far dimmer than our Sun, glowing with a distinct reddish hue. Because of its lower temperature, the habitable zone around a red dwarf is much closer in than it is around a Sun-like star. Kepler 186f orbits its star at a distance that would place it somewhere between Mercury and Venus in our own solar system. But because the star itself is so much cooler, this proximity lands the planet perfectly in that temperate, life-friendly region. It completes one full orbit in just 130 days. One of the most exciting aspects of this discovery is the planet's size. Based on the amount of starlight it blocks during its transit, astronomers calculated its radius to be just 1.1 times that of Earth. This was a critical finding. A planet significantly larger than Earth would likely have accumulated a thick, crushing hydrogen and helium atmosphere, becoming a mini Neptune, a type of world utterly hostile to life as we know it. But a planet with a radius so close to Earth's almost certainly has a similar rocky composition, with a solid surface where water could pool and landscapes could form. This similarity, however, comes with some profound and fascinating differences. The star it orbits dictates a very different kind of environment. If you were standing on the surface of Kepler 186f, the sky would not be bright blue. The parent star, being a red dwarf, would cast a dim, reddish light over the landscape, creating a permanent, serene twilight. Because the planet is so close to its star, it is likely tidally locked, much like our moon is to Earth. This means one side of the planet would be in perpetual, sweltering daylight, while the other would be trapped in an eternal, frigid night. For a long time, scientists thought tidal locking would be a death sentence for the possibility of life, as the day side would overheat and the night side would freeze solid. However, more recent climate models suggest that a reasonably thick atmosphere could circulate heat around the planet, creating a temperate band along the terminator line, the narrow twilight zone between the two hemispheres. In this region, conditions could be stable enough for liquid water to exist, a world of eternal dawn and dusk. The potential for an atmosphere is the single greatest question mark hanging over this world. Red dwarf stars are notoriously volatile, especially in their youth. They are prone to frequent and powerful stellar flares, eruptions that blast out intense ultraviolet and X-ray radiation. This fury could potentially strip away the atmosphere of a nearby planet like Kepler 186f over billions of years, leaving it a barren, airless rock. Yet, if the planet has a strong magnetic field like Earth's, that field could act as a protective shield, deflecting the worst of the stellar onslaught and allowing an atmosphere to persist. The presence or absence of that magnetic shield is the difference between a world that could host a shallow ocean or a few hardy microbes, and a world that is a silent, irradiated desert. While we currently lack the telescope technology to analyze the atmosphere of a planet so small and distant, the mere existence of Kepler 186f is a beacon of hope. It told us that Earth-sized planets in habitable zones are out there, and it paved the way for the discovery of even more promising candidates like those in the TRAPPIST-1 system. It transformed the search for life from a question of if such worlds exist to a question of how many, fueling our imagination and driving the development of the next generation of space telescopes that will one day peer into their air and seek the chemical signatures of a living world. Now let's dive into a world that redefines the very meaning of an ocean. Imagine a planet not just covered in water, but one that is almost entirely water itself, a global deep-sea abyss with no land in sight. This is GJ 1214b, a mysterious water world located just 40 light-years away in the constellation Ophiuchus. Discovered in 2009, this exoplanet immediately captured the attention of astronomers because of its perplexing and contradictory nature. It's classified as a super-Earth, but this term is a bit misleading. While it has a mass about 6.5 times greater than Earth and a radius nearly 2.5 times larger, it is not a rocky world like our own. Instead, its exceptionally low density tells a different story. This planet is far too light for its size to be made of rock and metal alone. The numbers pointed to a composition that is overwhelmingly water. This isn't an ocean world with familiar coastlines and continents. The sheer scale of its aquatic nature is almost impossible to comprehend. Scientists believe the planet could be composed of more than 50% water by mass, a staggering figure when you consider that Earth, the blue planet, is only about 0.02% water by mass. This means GJ 1214b likely has a relatively small rocky core, similar to Earth's in size, but that core is utterly dwarfed by a surrounding global ocean that is hundreds, perhaps even thousands of miles deep. To put that in perspective, the deepest part of Earth's ocean, the Mariana Trench, plunges just under 7 miles. On GJ 1214b, the ocean is so deep that the very water at the bottom would be subjected to pressures millions of times greater than what we experience at sea level. Under such incredible forces, water stops behaving like the liquid we know. It gets squeezed into exotic, high-pressure states known as hot ice or superionic water. In this bizarre form, the water molecules break apart, with the oxygen atoms locking into a rigid crystalline lattice, a solid, while the hydrogen ions flow through it like a liquid metal. So, while the surface might be a churning, superheated sea, the planet's interior could be a shell of this surreal, solid ice that remains frozen despite the scorching temperatures, all because of the immense pressure from the ocean above it. The atmosphere of this world is just as alien as its interior. Observations from the Hubble Space Telescope revealed that GJ 1214b is shrouded in a thick, global, and permanent layer of high-altitude clouds or haze. This isn't the puffy, water vapor clouds of Earth. This is a dense, steamy blanket that completely obscures our view of the ocean below. The planet orbits extremely close to its small, cool red dwarf star, completing a year in just 38 hours. This proximity creates a surface temperature estimated at over 400 degrees Fahrenheit. At that heat, the upper layers of the global ocean are constantly boiling, feeding a thick, water vapor-dominated atmosphere. The haze is likely composed of more complex chemicals, perhaps salts or other compounds that have evaporated from the ocean, creating a perpetual, oppressive steam bath. The pressure at what we might call the surface of this ocean, the point where the liquid meets the thick atmosphere, would be crushing, hundreds of times greater than Earth's atmospheric pressure. If a probe could somehow descend through the clouds, it would find itself not in open air, but plunging directly into a hot, dark, soupy sea, with visibility dropping to zero almost instantly, descending into an abyss where the very nature of matter becomes strange and unfamiliar. The existence of GJ 1214b raises profound questions about the diversity of planetary formation. How does a world with so much water come to be? There are two leading theories, both fascinating. The first is that it formed much farther out in its stellar system, in the cold regions beyond the frost line where water ice is plentiful like a cosmic snowball. Then, through gravitational interactions, it migrated inward to its current scorching orbit. The second theory is that it formed directly from water-rich material in the protoplanetary disk, accreting an enormous amount of ice and gas from the very beginning. Regardless of its origin story, GJ 1214b stands as a powerful example of a whole class of planets that are entirely absent from our solar system, the mini-Neptunes. These are worlds larger than Earth but smaller than Neptune, with thick gaseous envelopes and no solid surface as we know it. GJ 1214b blurs the line between a gas giant and a terrestrial planet, a world that is more ocean than anything else. A haunting and beautiful reminder that the family of planets in our galaxy is far more diverse and far more liquid than we ever could have guessed. If you thought the conditions on CoRo T7b or WASP 76b were extreme, they are merely a warm summer's day compared to the unadulterated stellar fury of our next destination. Behold Kelt 9b, a gas giant that holds the undisputed title of the hottest planet ever discovered, a world so profoundly scorched that it defies the very definition of a planet and borders on being a star itself. Located 670 light-years away in the constellation Cygnus, this planet orbits a blue Type star known as Kelt 9, which is nearly twice the size of our Sun and burns at a surface temperature of over 17,000 degrees Fahrenheit. But the true engine of this planet's hellish existence is its orbit, a path so inconceivably close that the planet is practically skimming the star's outer atmosphere. A single year on Kelt 9b, one full trip around its star, flashes by in just 1.5 Earth days. This intimate proximity subjects the planet to a relentless, unimpeded barrage of stellar radiation, baking its day side to a temperature of approximately 7,800 degrees Fahrenheit. To truly grasp that number, consider that the surface temperature of our Sun is around 10,000 degrees. This means the day side of Kelt 9b is actually hotter than the surface of some red dwarf stars. We are looking at a planet that is literally hotter than a star. This level of heat has consequences that sound more like particle physics than planetary science. On a normal world, the atmosphere is made of molecules, combinations of atoms like water, carbon dioxide, or molecular hydrogen. But at 7,800 degrees, the very concept of a molecule becomes untenable. The immense thermal energy is simply too great for atomic bonds to hold. On the permanent day side of Kelt 9b, molecules cannot exist. When hydrogen gas, the primary component of its atmosphere, is blasted by the star's radiation, it is torn apart into its constituent atoms. The atmosphere is not a soup of familiar gases, but a plasma of individual, dissociated atoms constantly being battered by high-energy ultraviolet radiation. This creates a bizarre and violent environment where the very ingredients for a stable atmosphere are perpetually being broken down into their most fundamental parts. There is no weather here, no clouds or storms as we understand them. There is only a maelstrom of atomic particles superheated to a state of constant, raging agitation. This planetary inferno is not a stable, long-term resident of its solar system. It is a cosmic prisoner on death row, undergoing a slow and spectacular execution. The intense heat from the star doesn't just cook the planet, it is actively boiling it away into the void of space. The process, known as hydrodynamic escape, works like a giant kettle left on the highest possible setting. The high-energy ultraviolet photons from the star slam into the planet's atmosphere, transferring so much energy to the atoms, particularly the light hydrogen atoms, that they achieve escape velocity. These atoms are then ripped from the planet's gravitational grip and stream off into space, forming a gigantic comet-like tail. Astronomers estimate that Kelt 9b is losing mass at a phenomenal rate, shedding up to 10 million tons of its atmosphere every single second. This creates a glowing, tenuous cloud of evaporated planetary material that trails behind the world as it speeds through its orbit. The planet is essentially being systematically disassembled by its own sun, a process that will ultimately leave behind nothing but a scorched, barren core, a ghost of the gas giant it once was. The discovery of such a violently ephemeral world forces us to reconsider the life cycles of planets and pushes the boundaries of where we thought planets could even form. It seems to be the remnant of a gas giant that migrated too close to its brilliant and unforgiving host, a celestial Icarus that flew fatally close to a stellar flame, condemned to blaze with impossible brilliance for a cosmic instant before vanishing entirely. Just when you thought we had seen every kind of orbital oddity, the universe presents us with a new form of planetary chaos, not from fire or ice, but from a fundamental instability in the very way these worlds spin. Our journey now takes us to two remarkable planets, Kepler 64b and Kepler 413b, celestial bodies that don't simply orbit their stars. They wobble and tilt with such dramatic flair that their seasons and climates are in a state of perpetual, dizzying flux. First, let's visit the remarkable system of Kepler 64b. This world holds the distinction of being part of a quadruple star system, a fact that alone places it in a rare category of cosmic weirdness. Imagine a planet that looks up to see not one, not two, but four suns in its sky. While two of these stars form a tight central binary that the planet orbits, the other two stars orbit this central pair from a much greater distance, appearing as brilliant, distant companions. But the true strangeness of Kepler 64b lies in its orientation. Its rotational axis, the imaginary line through its north and south poles, is tilted at an extreme angle. On Earth, we have a stable axial tilt of about 23.5 degrees, which gives us our predictable spring, summer, fall, and winter. The tilt of Kepler 64b is so severe that its poles are practically pointing toward its orbital plane. This means that over the course of its long orbit, which lasts about 138 days, the planet's hemispheres experience wild swings in solar exposure. For decades, one pole might be plunged into constant, searing daylight, while the other endures an endless, deep freeze night. Then, as the world continues its slow, wobbly procession, the roles would gradually reverse, with the former winter pole slowly turning to face the stellar fires and baking under an unrelenting sun. This procession, the slow gyration of a planet's axis, is something Earth experiences over a Chinese letter of 26,000 years. But on Kepler 64b, this wobble is far more pronounced and rapid. The combined gravitational tug of war from its multiple suns constantly torques the planet, pulling on its bulge and causing its axial tilt to change over time in a complex, unpredictable dance. The result is a climate without any recognizable pattern, where seasonal changes are not annual events but chaotic, multi-decadal upheavals, making the very concept of a stable environment impossible. Now consider an even more extreme example of this planetary instability, Kepler 413b. Located about 2,300 light-years away in the constellation Cygnus, this Neptune-sized world orbits a pair of orange and red dwarf stars. What makes this planet a true standout, even among tilted worlds, is the sheer speed of its wobble. The precession of its spin axis is so incredibly fast that it completes a full wobble cycle in just 11 years. To visualize this, think of a spinning top that is about to fall over, its handle tracing a wide, looping circle in the air. Now, imagine that entire wobble cycle, which takes Earth 26 millennia, happening in little more than a decade. This has a breathtaking and chaotic effect on the planet's climate. Over a mere 11-year period, the tilt of the planet's axis can vary so wildly that the location of its tropics and polar circles shifts dramatically. A region that was once a temperate zone could, within a few years, be shifted directly into the path of constant, scorching sunlight, before being swung just as rapidly into a deep polar winter. The planet's seasons wouldn't just be extreme, they would be utterly erratic and unpredictable, changing their character and intensity on a timescale that is incredibly short from a geological perspective. The discovery of these worlds was a masterclass in data analysis. Astronomers using the Kepler telescope detected them by the transit method, watching for the tiny dip in starlight as each planet passed in front of its host stars. But the light curves for these planets were messy and confusing. The transits of Kepler 413b, for instance, would appear for a while, then vanish for hundreds of days, only to reappear again. This was not the clean, periodic signal of a stable orbit. The reason was the planet's rapid precession, which was constantly changing the orientation of its orbit from our viewpoint. Think of it as trying to watch a swing from the side. You see the person moving back and forth clearly. But if the entire swing set were slowly rotating, there would be times when the swing was moving toward you and away from you, making it seem to disappear from your side on view. That's precisely what happens with Kepler 413b. Its wildly precessing orbit moves in and out of our line of sight to the stars, causing the transits to come and go in a long-term cycle. This bizarre signal was the key that unlocked the secret of its unstable spin. For any form of life that could theoretically arise on such a world, existence would be a constant, desperate struggle against a climate gone mad. The very foundations of an ecosystem, predictable growing seasons, stable temperatures, and reliable water cycles, would be impossible to establish. Plants and animals that evolved to handle one set of conditions would be regularly and ruthlessly tested by a completely different set, all within a single generation. These tilted and wobbly worlds are a stark demonstration that a planet's placement in the habitable zone is only one part of the equation for life. Without the stabilizing influence of a large moon, like the one that steadies Earth's tilt, or a calm gravitational environment, a planet can become a chaotic gyroscope, its climate a roller coaster with no end in sight, forever at the mercy of the gravitational forces that twist it through space. While the chaotic wobble of Kepler 413b creates unpredictable seasons, there exists another, even more dramatic way for a planet's climate to swing between extremes. This brings us to a pair of worlds that don't just tilt erratically, but whose very paths through space are looped and oval shaped in the most extreme way imaginable. Journey with us to HD 20782b and HD 80606b, the eccentric giants, two planets whose orbits are less like neat circles and more like cometary paths, catapulting them between blistering inferno and deep space freezer on a regular, terrifying schedule. First, let's meet HD 20782b, a world that holds a truly spectacular record. Located about 117 light-years away in the constellation Fornax, this planet has the most eccentric orbit of any known exoplanet around a main sequence, Sun-like star. To understand its path, picture a child's drawing of an orbit, a long, skinny oval. Its orbital eccentricity is a staggering 0.96, where a perfect circle is 0 and a parabola, which would fling the planet away forever, is 1. This means HD 20782b spends the vast majority of its year, which lasts 597 Earth days, drifting in the cold, dark outer reaches of its system, an incredible 2.5 times farther from its star than Earth is from the Sun. For most of its long year, this Jupiter-sized world is a frozen, dormant giant, its atmosphere contracting in the deep chill, a silent orb in the void. But then, the physics of its orbit takes over and it begins its plunge. Like a roller coaster car cresting the highest hill, it accelerates on its terrifying dive toward its star. It screams inward, whipping around its star at a periastron, the point of closest approach, that is a mere 0.06 times the Earth-Sun distance. That is 6 times closer to its star than Mercury is to our Sun. The transition is not gradual, it is a violent, sudden shock. In a matter of days, the planet goes from the deep freeze of the outer system to being closer to its star than the scorched surface of Mercury. The stellar flux, the amount of energy it receives, increases by a factor of over 100 in an incredibly short time. The surface temperature on its Sun facing side skyrockets from a few hundred degrees below zero to a searing 2,700 degrees Fahrenheit in a flash. This isn't a seasonal change, it is a global atmospheric bomb going off. The thin layers of its atmosphere that were frozen onto the surface during the long winter instantly vaporize, creating a temporary, puffed up, and incredibly hot gaseous envelope. The planet's outer layers expand violently from the heat, and astronomers theorize that this rapid heating could trigger colossal, global shockwaves that propagate through the atmosphere at supersonic speeds, generating storms that would dwarf the Great Red Spot of Jupiter. Then, just as quickly as it arrived, the planet completes its sharp turn around the star and begins its long, slow journey back out into the cold, its atmosphere cooling and recollapsing as it retreats once more into the deep freeze. Now consider its cousin, HD 80606b, located 190 light-years away in the constellation Ursa Major. This world offers us an even more detailed and observed portrait of this kind of orbital madness. Its eccentricity is a similarly dramatic 0.93, and its 111-day orbit provides a perfect laboratory for watching a planetary atmosphere in crisis. NASA's Spitzer Space Telescope was able to observe this planet during a 20-hour period as it made its closest approach to its star, and the data it gathered is a breathtaking time lapse of a world undergoing an apocalypse. As the planet approached its star, the temperature on its day side soared from about 900 degrees Fahrenheit to a staggering 2,200 degrees in just 6 hours. That is a temperature increase of over 1,500 degrees in the time it takes to watch a long movie. The thermal shock was so extreme that the planet's atmosphere couldn't respond calmly. The side facing the star heated up so rapidly and so intensely that it created a colossal, supersonic jet of heated air that raced from the day side to the night side. This produced a truly monstrous storm, a single planet-encompassing hurricane of superheated gas, complete with shockwaves that reverberated around the entire world. The planet itself, under the immense gravitational strain of being so close to its star, is stretched and squeezed, its very structure flexing with the tidal forces, generating massive internal friction and heat. This world doesn't just get hot, it is physically tortured and whipped into a global frenzy every time it swings past its sun. The existence of these eccentric giants poses a fascinating puzzle for astronomers. How do such massive planets end up in these comet-like orbits? The prevailing theory is gravitational scattering. In their youth, these systems may have contained multiple giant planets. Through close gravitational encounters, one planet was flung inward onto a chaotic path, while another might have been ejected into interstellar space entirely, becoming a rogue planet. HD 20782b and HD 80606b are the survivors of these ancient planetary billiards games, the lone winners of a gravitational duel that left them forever trapped on a roller coaster ride between fire and ice, a permanent testament to the violent and dynamic processes that shape planetary systems long after they form. As we pull our gaze back from the chaotic orbits of eccentric giants, we arrive at a stellar neighborhood that feels almost impossibly cozy and orderly by comparison. Nestled just 40 light-years from Earth in the constellation Aquarius is a star system that has fundamentally reshaped our search for life beyond our solar world. This is the TRAPPIST-1 system, a family of not one or two, but 7 rocky planets, each one remarkably similar in size to Earth. What makes this system so extraordinary is its sheer compactness and the tantalizing possibility it represents. All 7 of these worlds orbit an ultra-cool red dwarf star, a celestial body so small and faint that it is barely larger than the planet Jupiter and glows with a dim, deep crimson light. This star's gentle output creates a habitable zone that is incredibly close in, and within that snug region, all 7 planets have found their home. Their orbits are so tight that the entire system could easily fit within the distance between our Sun and its innermost planet, Mercury. In fact, if you were standing on the surface of the outermost world, TRAPPIST-1H, the parent star would appear about 3 times larger in the sky than our Sun does from Earth, a great, brooding red orb casting a perpetual, bloody twilight over the landscape. The dynamics of this system are a celestial dance of exquisite precision and harmony. Because the planets are packed so closely together, their years are incredibly short. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 Earth days, while the outermost, TRAPPIST-1h, takes about 20 days. This proximity means the planets exert significant gravitational influence on one another. As they orbit, they engage in a phenomenon known as orbital resonance. This is a rhythmic gravitational lockstep where the orbital periods of the planets are related by ratios of small whole numbers. For example, for every 2 orbits the innermost planet makes, the next one out makes 1. For every 3 orbits of that second planet, the third makes 2, and so on. This intricate chain of resonances keeps the system stable over vast stretches of time, preventing the planets from gravitationally bullying each other out of their orbits. It's a delicate, self-regulating clockwork that has likely persisted for billions of years, a testament to the elegant mechanics that can emerge from cosmic chaos. From the surface of any one of these worlds, the other 6 would be prominent features in the sky, often appearing as vivid, star-like points brighter than Venus does from Earth, and sometimes even passing directly in front of one another in a constant, silent ballet of transiting shadows. This compact arrangement, however, comes with a significant consequence for the potential climates of these worlds. Given their extreme proximity to their star, it is almost certain that all 7 planets are tidally locked. Just as our moon always shows the same face to Earth, each TRAPPIST-1 world likely has a permanent day side, bathed in the constant, dim red light of the star, and a permanent night side, shrouded in eternal, deep freeze darkness. For a long time, scientists thought this would be a death knell for habitability, envisioning a scenario where the day side would become a scorching desert and the night side a frozen wasteland, with only a narrow, razor-thin twilight strip offering any hope for temperate conditions. However, sophisticated climate models have revealed a more optimistic picture. A key factor is the potential presence of an atmosphere. If these planets have retained a substantial atmosphere, something similar to Earth's or even a thicker one like Venus's, that air can act as a global heat transfer system. Winds and ocean currents could circulate efficiently, carrying warmth from the hot day side over to the frigid night side and pulling cooler air back again. This process could potentially create large, stable regions with moderate temperatures, rather than just a thin sliver of habitability. The very oceans themselves, if they exist, would be powerful engines for distributing this heat, potentially creating global climates that are surprisingly Earth-like despite the strange fixed orientation of their star. This brings us to the central, burning question that makes the TRAPPIST-1 system the focus of such intense scientific scrutiny. Which of these 7 siblings could actually support life? The most promising candidates are the 3 planets that sit squarely within the star's conservative habitable zone, TRAPPIST-1e, F, and G. This is the region where, given the right atmospheric conditions and pressure, liquid water could theoretically exist on their surfaces. TRAPPIST-1e, in particular, has emerged as a favorite. It is a world almost identical in size to Earth and receives a similar amount of stellar energy from its red sun as our planet does from our yellow one. Its density suggests it is a rocky world with an iron core, and it could very well have liquid water oceans. It is, in many ways, the most Earth-like exoplanet we have yet discovered. TRAPPIST-1F and G are slightly larger and cooler, receiving less stellar flux, making them potential snowball or water world candidates where global ice sheets or deep oceans might dominate the landscape. The inner planets B, C, and D are likely far too hot, their surfaces possibly scorched by an early, violent phase in the star's life, while the outermost H is probably a frozen ice ball. The ultimate answer to the question of habitability hinges almost entirely on one critical and still unknown factor: atmospheres. Red dwarf stars like TRAPPIST-1 are notorious for their tempestuous youth. In their first billion years, they are prone to frequent and colossal stellar flares and eruptions that blast out intense ultraviolet and X-ray radiation. This fury could have stripped away the primordial atmospheres of all 7 planets, leaving them as barren, airless rocks. The key to their survival would have been a strong magnetic field, like the one generated by Earth's churning iron core, which can deflect such stellar assaults. The current race in astronomy is to detect and characterize the atmospheres of these worlds, most notably with the James Webb Space Telescope. Webb's powerful infrared eyes are capable of analyzing the starlight that filters through a planet's atmosphere during a transit. By dissecting this light, scientists can search for the chemical fingerprints of key molecules. The dream, of course, is to find a combination of gases that suggests biological activity, a biosignature. The most promising of these is the simultaneous presence of oxygen and methane, 2 gases that normally react with and destroy each other quickly unless there is a constant source like life replenishing them. Other targets include carbon dioxide, water vapor, and the absence of certain gases that would indicate an atmosphere has been completely stripped away. The search is on, and each observation brings us closer to understanding whether this compact family of worlds is a septet of sterile rocks or a collection of living, breathing worlds huddled around their faint red sun. The TRAPPIST-1 system is more than just a record-breaking discovery. It is a living laboratory, a testbed for our theories of planetary formation and habitability, and our best current hope for finding a second Earth, or perhaps even a second genesis of life in the vast, dark ocean of space. After contemplating the tightly packed family of worlds in the TRAPPIST-1 system, we now confront a planet that represents the polar opposite of a family, a lonely survivor of cosmic catastrophe. Imagine a world that should have been a gas giant, a behemoth like Jupiter or Saturn, but instead appears as a naked, exposed heart. This is TOI 849b, a celestial mystery located 730 light-years away, and it presents astronomers with a profound puzzle. Discovered by NASA test satellite, this planet was immediately flagged as an anomaly. Its size, about 3.4 times the width of Earth, suggested it should fall into the common category of mini-Neptunes, a type of world with a thick, gaseous envelope surrounding a smaller core. But when astronomers measured its mass, the numbers told a completely different story. TOI 849b packs an incredible 40 Earth masses into that relatively small frame. This gives it an astonishingly high density, far greater than any gas-dominated world. The inescapable conclusion is that we are not looking at a typical planet, but at something unprecedented, the exposed, stripped bare core of a former gas giant. The sheer density points to a composition of rock and metal, likely a colossal sphere of iron, nickel, and silicate rock, similar to the deep interior of Earth but on a monstrous scale. This is the planetary equivalent of an archaeological dig that has reached the foundational layer, revealing the primordial core that is usually hidden beneath thousands of miles of swirling hydrogen and helium. The existence of such an object raises the most compelling question. How did it get this way? How does a gas giant lose its entire atmosphere, the very thing that defines it? Scientists have developed several dramatic theories to explain this planetary undressing, and each scenario is more violent than the last. The leading hypothesis involves a catastrophic migration. TOI 849b orbits incredibly close to its Sun-like star, completing a full revolution in just 18 hours. This places its surface temperature at a scorching 2,700 degrees Fahrenheit. It's possible this world formed much farther out in its system, in the cold region where ice and gas are plentiful, and began its life as a proper Jupiter-like giant. But through gravitational interactions with other planets or the protoplanetary disk, it was forced inward on a spiral of doom. As it migrated into this blisteringly close orbit, the intense radiation and stellar winds from its host star began to bombard its outer layers. The planet's vast gaseous envelope, no longer held tightly by gravity in the face of such stellar fury, was violently boiled away and stripped off, leaving behind only the heavy, dense core that was able to withstand the onslaught. Think of it as a cosmic sandblasting on a planetary scale, where a star systematically erased the atmosphere of a giant world over millions of years. Another, even more spectacular theory suggests that TOI 849b might be the result of a giant impact. In the chaotic early days of its solar system, this gas giant could have collided with another massive planet in a cataclysmic event. The titanic energy released in such a collision would have been more than enough to blast the entire gaseous shroud off the planet, ejecting it into space and leaving the shattered, smoldering core behind. This would be a planetary version of a head-on collision that shears away the vehicle's body, leaving only the engine block. A third possibility is that TOI 849b never managed to acquire its gas envelope in the first place. It could be a failed gas giant, a world that grew its massive core of rock and metal late in the life of the protoplanetary disk, by which time most of the gas in the system had already dissipated. It was left as a colossal embryonic core, a planet that never got to fulfill its destiny of becoming a giant. Regardless of which theory proves correct, the existence of TOI 849b is a game-changer for planetary science. It provides us with a unique, natural laboratory to study the interior of a gas giant, something we can never do directly. By analyzing its composition and structure, we can test our models of how planetary cores form and evolve. This single, bizarre world offers a direct window into the violent processes of planetary migration, stellar irradiation, and gravitational scattering that sculpt solar systems. It stands as a stark and silent monument to the forces of creation and destruction, a ghost of a giant that once was, now forever circling its star as a bare, metallic testament to the chaos of cosmic evolution. But what if the most promising world for life isn't a twin of Earth, but something entirely different? A completely new class of planet that could harbor life in a way we had never before seriously considered. This brings us to K218b, a world that has ignited the imaginations of astrobiologists and redefined the boundaries of the habitable zone. Located just 124 light-years away in the constellation Leo, this planet isn't a small, rocky super-Earth like those in the TRAPPIST-1 system. It's something in between, a mini Neptune with about 8.5 times the mass of Earth and 2.5 times its radius. For years, planets of this size were largely written off in the search for life. Their significant mass and size suggested they were likely to be shrouded in thick, crushing layers of hydrogen and helium gas, with no solid surface, making them more akin to small, inhospitable versions of Neptune. However, groundbreaking observations of K218b have turned this assumption on its head, revealing it to be the first known example of a potentially Hycean world, a term derived from hydrogen and ocean. The concept of a Hycean world is a revolutionary one in planetary science. It describes a planet with a massive, hydrogen-rich atmosphere surrounding a vast, global liquid water ocean. Instead of a rocky seafloor like Earth's, the ocean on a Hycean world would be underlaid by a thick layer of high-pressure ice, with a small, rocky or metallic core at the very center. What makes K218b such a compelling candidate for this classification are the stunning results from the James Webb Space Telescope. Webb's unparalleled infrared sensitivity allowed it to analyze the starlight filtering through the planet's atmosphere during a transit, and the chemical signatures it found were extraordinary. The atmosphere of K218b was found to be rich in carbon dioxide and methane, but the real bombshell was the clear, confident detection of dimethyl sulfide, or DMS. On Earth, DMS is a gas produced almost exclusively by biological processes, specifically by phytoplankton in our oceans. There are no known non-biological processes that can produce DMS in significant quantities in a planetary atmosphere. While scientists are quick to emphasize that the detection is not yet conclusive and requires further verification, the very possibility has sent ripples of excitement through the scientific community, as it represents one of the most promising potential biosignatures ever detected on an exoplanet. The environment on K2-18b would be unlike anything we have in our solar system. It orbits within the habitable zone of its cool red dwarf star, but its thick hydrogen atmosphere creates a powerful greenhouse effect. This keeps the planet much warmer than its distance from the star would otherwise suggest, but it also results in immense surface pressure. If you could descend through its hazy, pinkish atmosphere, you would not find a solid surface to land on. Instead, you would eventually reach a boundary where the atmosphere transitions into a global, planet-wide ocean, likely hundreds of miles deep. The pressure at the top of this ocean would be crushing, dozens or even hundreds of times greater than the pressure at the bottom of Earth's Mariana Trench. Yet, the temperature at this ocean-atmosphere interface could be just right for liquid water to exist. This creates a truly unique habitat. The hydrogen-rich atmosphere would act as a giant blanket, trapping heat and preventing the water from freezing, while the global ocean itself could be a nurturing medium for life. Because the planet is likely tidally locked with one side always facing the star, there might be a permanent dayside ocean kept warm by the star's faint glow, and a much colder nightside ocean with potentially complex currents circulating between them. The discovery of K2-18b and its potential Hycean nature dramatically expands the cosmic real estate we consider potentially habitable. For decades, the search for a second Earth was the primary goal. But K2-18b suggests that life could arise and thrive on worlds that are nothing like our own planets that are larger, with atmospheres dominated by hydrogen and with oceans that have no land in sight. If life can exist in the deep, dark, high-pressure trenches of Earth's oceans, then why not in the global sea of a Hycean world? The presence of carbon-bearing molecules like methane and carbon dioxide, and the tantalizing hint of dimethyl sulfide, points to a world that is not just habitable in theory, but one that may actually be inhabited. This shifts the paradigm, suggesting that the signs of life we should be looking for are not just those found on Earth like planets, but also within the thick, steamy atmospheres of water-rich mini-Neptunes. K2-18b stands as a beacon of cosmic possibility, a world that was once dismissed as just another gas dwarf, but now emerges as one of the most promising and intriguing targets in our entire galactic neighborhood. A place where an entirely alien form of biology might be flourishing beneath a sky of hydrogen in an endless, dark, and life-giving sea. After traveling across thousands of light years to visit frozen super-Earths and tortured gas giants, our journey brings us at last to our own cosmic backyard, to a world that is literally our next-door neighbor in the vast expanse of the galaxy. This is Proxima Centauri b, an exoplanet orbiting the closest star to our own Sun, a faint red dwarf just 4.24 light-years away. Its discovery in 2016 sent shockwaves through the scientific community and the public imagination alike, not just for its proximity, but for its tantalizing profile. Here, in our nearest stellar system, sits a world with a mass remarkably similar to Earth's, comfortably nestled within the habitable zone of its star. The implications were staggering, the very first potentially Earth-like planet we could ever hope to study in detail, and perhaps even one day reach, was right on our doorstep. The star it calls home, Proxima Centauri, is part of the three-star Alpha Centauri system, but it is the smallest and faintest of the trio. It is a red dwarf, a class of star that makes up about 75% of all stars in the Milky Way. These stars are frugal with their fuel, burning for trillions of years, but they are also dim and cool. Because of this low energy output, their habitable zone, the orbital region where temperatures might allow for liquid water, is incredibly close to the star. Proxima Centauri b exemplifies this, orbiting 20 times closer to its star than Earth does to the Sun. A full year on this world, one complete trip around its Sun, flashes by in just 11.2 Earth days. This extreme proximity has a profound consequence. The planet is almost certainly tidally locked. This means one hemisphere of Proxima b, the day side, permanently faces its dull red sun, locked in an endless, simmering daylight. The other hemisphere, the night side, is forever turned away, trapped in the deep, permanent freeze of space. This configuration alone would create a world of extreme climate contrasts, but the true challenge for potential life on Proxima Centauri b comes from the volatile nature of its parent star. Red dwarfs, especially in their youth, are notoriously tempestuous. Proxima Centauri is a flare star, prone to sudden, violent eruptions that can, in a matter of minutes, double its brightness. These are not like the solar flares our Sun occasionally produces. These are cataclysmic events on a stellar scale. A typical flare from Proxima Centauri can unleash bursts of ultraviolet and X-ray radiation thousands of times more powerful than anything our Sun emits. For a planet like Proxima b, orbiting so close, these flares deliver a devastating one-two punch. First, the initial blast of high-energy radiation would be strong enough to strip away a planet's atmosphere over time, eroding it molecule by molecule through a process known as atmospheric erosion. Second, these flares are often accompanied by coronal mass ejections, colossal bubbles of stellar plasma and magnetic field that are hurled into space. If such an ejection were to hit Proxima b, it could overwhelm any protective magnetic field the planet might have and directly bombard the surface with lethal radiation, effectively sterilizing the dayside hemisphere. The question of whether Proxima Centauri b could actually host life, then, becomes a race between two powerful forces: the planet's ability to hold onto a protective atmosphere and the star's relentless fury trying to tear it away. The planet's Earth-like mass is a point in its favor, as its gravity should be strong enough to hold onto a substantial atmosphere, assuming one ever formed. Furthermore, if Proxima b has a molten, churning iron core like Earth's, it could generate a global magnetic field. This magnetic shield would be its greatest defense, acting like an invisible umbrella that deflects the star's most dangerous charged particles, channeling them safely away from the atmosphere and surface. Without such a shield, Proxima b is likely a barren, irradiated rock, but with one, the story becomes far more interesting. A thick atmosphere could work to distribute heat from the hot day side to the cold night side, potentially creating a wide, temperate ring in the twilight zone between the two hemispheres, a place of eternal sunrise or sunset where liquid water could theoretically pool on the surface. Some climate models even suggest that a global ocean could effectively transfer heat around the entire planet, preventing the night side from freezing solid entirely. The intense, unpredictable flare activity, however, presents a unique set of evolutionary challenges. Any life that attempted to gain a foothold on the surface would need to be incredibly resilient, perhaps existing deep underground or underwater to shield itself from the periodic radiation blast. Alternatively, life might find a way to thrive in the planet's atmosphere or in subsurface aquifers, completely isolated from the violent tantrums of the star above. The very fact that we are now asking these questions about a specific Earth-mass world just over 4 light-years away is a testament to how far exoplanet science has come. Proxima Centauri b is more than just another entry on our list of strange planets. It is a tangible destination. It is the focal point of ambitious projects like Breakthrough Starshot, which aims to send tiny, laser-propelled probes to the Alpha Centauri system within a generation. It is the prime target for the next generation of giant telescopes, which will one day attempt to directly image this nearby world and analyze the composition of its atmosphere, searching for the telltale signs of water vapor, oxygen, or even methane. While it may not be the paradise we once envisioned, Proxima Centauri b represents something equally profound, a nearby laboratory for understanding the limits of life and the true nature of habitable worlds, a constant reminder that the greatest mysteries in the universe are sometimes hiding in plain sight, right next door. As we extend our view from the planets huddled close to their stars to the vast, dark frontier of our own solar system, we find that the cosmic oddities do not end at the orbit of Neptune. Far beyond the familiar 8 planets, in the cold and silent realm known as the scattered disk, a compelling astronomical detective story is unfolding: the hunt for a hidden giant, a hypothetical world we call Planet 9. The evidence for this unseen planet does not come from a telescope capturing its faint light, but from the peculiar, clustered orbits of a group of small, icy bodies. These distant objects, known as trans-Neptunian objects or TNOs, should, in theory, have orbits that are randomly oriented around the Sun. Yet, detailed observations have revealed something deeply strange. A collection of these objects, with their elongated paths taking them hundreds of astronomical units from the Sun, have orbits that seem to be herded. Their points of closest approach to the Sun, their perihelia, are mysteriously grouped together in space, and their orbits are tilted in a similar direction, as if an invisible shepherd is guiding their paths through the void. This gravitational choreography is the primary clue that points to the existence of a massive, undiscovered planet. The mathematical models created to explain these orbital oddities suggest a compelling profile for this hidden world. Planet 9 is not thought to be a small, rocky body like Pluto, but a true giant, a super-Earth or mini-Neptune with a mass estimated to be between 5 and 10 times that of our own planet. Its orbit, however, would be unlike anything else in our solar system. Instead of a relatively circular path, this world would follow a tremendously elongated and tilted orbit, taking it on an epic journey around the Sun. At its closest approach, it might come within 200 or 300 astronomical units from the Sun, still far beyond Neptune, but at its most distant point, it could swing out to a staggering 600 or even 1,200 astronomical units, placing it deep in the inner Oort cloud, the vast reservoir of icy bodies that surrounds our solar system. A single year on this world, one complete orbit, could take an almost inconceivable 10,000 to 20,000 Earth years to complete. The search for this phantom planet is one of the great modern challenges in astronomy. Because its proposed orbit is so vast and its distance so great, it would reflect very little sunlight, making it incredibly faint and difficult to spot. Furthermore, astronomers have to scan enormous swaths of the sky to find it, as its precise location is unknown. This is not a simple task of pointing a telescope at one spot. It is a meticulous pixel-by-pixel examination of the deepest archival data from powerful telescopes like Subaru in Hawaii and the Dark Energy Survey in Chile. Researchers are looking for a slow-moving dot of light shifting its position against the fixed background of stars over nights, weeks, and months. The challenge is compounded by the fact that at such incredible distances, even a massive planet moves very slowly across our line of sight, its motion measured in arcseconds per hour rather than the more obvious drift of closer asteroids or comets. It is a painstaking process of elimination, ruling out known objects and chasing down the most subtle of anomalies in the data. If Planet 9 does indeed exist, its characteristics would be as bizarre as its proposed orbit. Imagine a world that spends the overwhelming majority of its epoch-long year in the profound darkness and cold of deep space. With the Sun appearing as little more than an exceptionally bright star in its sky, its surface temperature would be only a few tens of degrees above absolute zero, a chill so deep that its atmosphere, if it has one, would likely be frozen solid, falling to the ground as a blanket of nitrogen, methane, and other exotic snows. For most of its multi-millennial orbit, it would be a silent, frozen fossil, a pristine relic from the earliest days of the solar system. However, as it makes its rare, slow swing through the inner part of its gargantuan orbit, this world could undergo a dramatic, temporary transformation. The weak but increasing warmth from the distant sun could cause its frozen atmosphere to sublimate, creating a transient, incredibly thin shroud of gas that lasts for a few thousand years before cooling and collapsing back to the surface as the planet retreats once more into the cold. This would give it a temporary, tenuous atmosphere that appears and disappears on a timescale longer than human civilization. The very existence of such a planet raises a fascinating question about its origin. How did a world this large end up in such a strange and distant orbit? It is unlikely to have formed in its current location, as the protoplanetary disk of dust and gas that surrounded our infant sun was probably not dense enough that far out. The leading theory is one of planetary migration and gravitational chaos. In the solar system's violent youth, the giant planets Jupiter, Saturn, Uranus, and Neptune may have shifted their positions. During this gravitational dance, the young planet 9 could have been gravitationally scattered outward by Jupiter or Saturn, flung into its extreme orbit. Alternatively, it is possible, though less likely, that Planet 9 is an exoplanet, a rogue world that was captured by our Sun's gravity after being ejected from its own native star system in the crowded stellar nursery where our Sun was born. If true, this would mean our solar system has been harboring an interstellar immigrant for billions of years, a cosmic visitor that settled in our most distant suburbs. The ongoing hunt is more than just a quest to fill a gap in a chart. It is a fundamental test of our understanding of the solar system's formation and dynamics. Finding Planet 9 would not just add a new world to our family, it would rewrite the history of our own cosmic neighborhood, revealing a past filled with gravitational upheavals and planetary ejections, and proving that even in our own backyard, the universe holds spectacular secrets waiting to be discovered. But as we contemplate the vast, lonely orbit of a hypothetical Planet 9, we must now venture even farther into the cosmic dark, to worlds that make such a distant orbit seem almost cozy by comparison. Imagine a planet with no sunrise, no sunset, and no star at all in its sky, a world completely untethered from the gravitational embrace of any sun, drifting forever through the cold, silent blackness of interstellar space. These are rogue planets, the ultimate nomads of the galaxy, and their existence paints a picture of a universe far more dynamic and at times violently chaotic than we ever imagined. For centuries, our definition of a planet was intrinsically linked to a star. It was a body that orbited a sun, but rogue planets shatter that definition entirely. They are solitary wanderers, ejected from their home solar systems during the gravitational turmoil of their youth, and now they travel the galaxy alone, illuminated only by the faint collective glow of the Milky Way. The story of how a planet becomes rogue is a dramatic tale of cosmic billiards. In the early, chaotic days of a young solar system, protoplanets are jostling for position within a swirling disk of gas and dust. When multiple giant planets form, their immense gravitational fields inevitably interact. In most cases, a stable configuration is found, but sometimes a close encounter can be catastrophic. One planet can gravitationally slingshot another, flinging it with such force that it achieves escape velocity, breaking free from its star's pull entirely and being ejected into the void. This is not a gentle process, it is a violent expulsion, a planetary eviction that sends the world on a one-way trip into the interstellar deep. Some rogue planets might even form on their own, in isolation, from collapsing clouds of gas and dust that were too small to ignite into stars. Failed stars or brown dwarfs that wander alone from birth. Detecting these dark, lone wanderers presents one of the greatest challenges in modern astronomy. Since they emit no light of their own and reflect no starlight, they are effectively invisible to traditional search methods like the transit technique, which relies on a planet passing in front of a star. Instead, astronomers have turned to a subtle and elegant phenomenon predicted by Einstein's theory of general relativity: gravitational microlensing. This technique relies on the fact that anything with mass, including a dark, rogue planet, warps the fabric of space-time around it. When such a planet drifts almost perfectly in front of a distant, background star from our viewpoint on Earth, its gravity acts as a tiny, natural lens. It bends and focuses the light from that faraway star, causing the star to temporarily brighten in a very specific way. The resulting light curve, a plot of the star's brightening and dimming, has a distinct, sharp peak that can last from a few hours to a couple of days, a fleeting signal that betrays the presence of an otherwise invisible mass. It is the ultimate cosmic detective work, finding a single, dark world by watching for its ghostly influence on the light of a star thousands of light years behind it. The environment on a rogue planet would be one of profound and absolute extremes. With no nearby star to provide warmth, the surface temperature would plummet to just a few degrees above absolute zero, a cold so intense that the very air we breathe would freeze solid into a blanket of nitrogen and oxygen snow. The surface would be shrouded in an eternal, starlit night, with the galaxy's band providing the only constant, faint illumination. Yet, despite this image of a frozen wasteland, there is a fascinating possibility that some rogue planets could, against all odds, harbor life. This potential hinges on the planet retaining an internal heat source from its radioactive core and the slow release of its primordial formation energy, much like Jupiter's moon Europa or Saturn's moon Enceladus in our own solar system. If a rogue planet were a water-rich world with a thick, insulating layer of ice on its surface, this internal heat could maintain a vast, global subsurface ocean in a liquid state. In the abyssal darkness beneath the ice, shielded from the radiation and hazards of space, microbial life, or perhaps something even more complex, could theoretically thrive around hydrothermal vents, drawing energy from the planet's interior chemistry rather than from sunlight. This concept radically expands the traditional habitable zone, suggesting that life could potentially exist in the most isolated and unexpected places, completely independent of any star. Recent surveys, like those conducted by the OGLE and KMTN projects, have suggested a staggering revelation: these lonely wanderers may not be rare anomalies. Data indicates there could be billions, perhaps even trillions, of rogue planets adrift in our galaxy alone, potentially outnumbering stars by a significant margin. This hidden population of dark worlds represents a mysterious and massive component of the galactic mass that has, until recently, remained almost entirely invisible to us. Their prevalence suggests that planetary ejection is a common, and perhaps even inevitable, part of the planet-forming process for many systems. The study of these nomads is still in its infancy, but upcoming missions like NASA and Nancy Grace Roman Space Telescope, which will conduct extensive microlensing surveys, are poised to uncover thousands of them. Each discovery will be a piece of a grand puzzle, helping us understand the violent early history of planetary systems, the stability of our own solar system, and the true diversity of worlds that fill the darkness between the stars. They are the silent, dark majority of our galaxy, a population of orphaned worlds on an endless journey, reminding us that the cosmos is filled with unseen wonders, drifting forever in the great starless expanse. Throughout history, our understanding of planets was limited to the few we could see in our own solar system. But the last few decades have utterly transformed that view, revealing a cosmos teeming with an almost unimaginable diversity of worlds. We have mapped these distant orbs by the shadows they cast and the wobbles they induce, inferring their existence through brilliant, indirect means. But the next great leap in this grand exploration is already underway. A shift from simply finding these worlds to truly understanding them, from knowing they are there to uncovering what they are actually like. The next chapter will be written not just by detecting planets, but by sniffing their air, analyzing their light, and searching for the faint chemical whispers of biology. This profound new era is being ushered in by a fleet of revolutionary observatories, both in space and on the ground, that are poised to turn these faint points of light into rich, dynamic worlds with stories to tell. At the forefront of this new age is the James Webb Space Telescope, an engineering marvel that has already begun to revolutionize our view. Unlike the Hubble Space Telescope, which primarily sees invisible and ultraviolet light, Webb is an infrared telescope, and this simple difference is its superpower. Infrared light is heat radiation, and it is the key to studying the atmospheres of exoplanets. When a planet transits in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere on its way to us. Different gases in that atmosphere absorb specific, unique colors of this starlight, leaving behind a barcode-like pattern of dark lines. Webb's incredible sensitivity in the infrared part of the spectrum allows it to read this barcode with unprecedented clarity, identifying molecules like water vapor, carbon dioxide, methane, and even more complex hydrocarbons. Its early observations of worlds like K218b, where it detected potential biosignatures, have given us just a taste of its power. Webb is not just looking for signs of habitability. It is actively conducting the first crude chemical censuses of these alien skies, searching for atmospheric imbalances that could point to processes we can't explain through geology and chemistry alone, processes that might just be biological in nature. While Webb peers from its stable orbit 1 million miles from Earth, a new generation of colossal ground-based telescopes is preparing to join the hunt, pushing the limits of engineering and optics. Projects like the extremely large telescope, the 30-meter telescope, and the giant Magellan telescope are, as their names suggest, on an entirely new scale. The ELT, being built in the high, dry Atacama Desert of Chile, will have a primary mirror a staggering 39 meters across, gathering 15 times more light than the largest optical telescopes operating today. This colossal light-gathering power, combined with advanced adaptive optics systems that use laser guide stars to correct for the blurring effects of Earth's atmosphere in real time, will allow these giants to achieve a level of clarity and sensitivity that was once the stuff of science fiction. Their primary mission in exoplanet science will be to move beyond the transit method. They aim to directly image planets, to literally separate the faint pinprick of light of a planet from the overwhelming glare of its host star. This is a monumental technical challenge, like trying to spot a firefly hovering next to a massive, brilliant searchlight from thousands of miles away. But by using sophisticated coronagraphs and other starlight-suppressing technologies, these telescopes will attempt to do just that. Once they have isolated that faint gleam, they can spread its light into a spectrum, analyzing the atmospheres of planets that do not transit from our viewpoint, vastly expanding the number of worlds we can study in detail. The synergy between these space-based and ground-based observatories will create a powerful partnership, each playing to its unique strengths. Webb and its planned successors, like the Nancy Grace Roman Space Telescope, excel at the delicate, ultra-precise spectroscopy of small, rocky worlds in the habitable zones of dim red dwarf stars. The giant ground-based telescopes, with their immense mirrors, will be able to conduct longer-term monitoring campaigns and capture direct images of younger, hotter, and more widely orbiting gas giants, studying the atmospheric dynamics of planets still glowing with the heat of their formation. Together, they will cross-check and validate each other's findings. A potential biosignature detected by Webb in the atmosphere of a transiting planet could be followed up by the ELT attempting to directly image that same world, confirming the signal and providing even more detailed data. This multi-pronged approach will allow us to move from studying individual, peculiar worlds to understanding the broader demographics of planetary atmospheres across the galaxy. We will begin to answer questions like, what are the most common atmospheric compositions for super-Earths? How do the atmospheres of planets around different types of stars evolve over time? is our own Earth's atmosphere with its persistent oxygen and methane, a cosmic oddity or a common signature of a living world. The ultimate goal, the holy grail of this entire endeavor, is the search for life itself. The telescopes of the next decade will be searching for biosignatures, combinations of gases in a planet's atmosphere that are difficult to explain without the presence of life. The simultaneous presence of large amounts of oxygen and methane is a powerful potential biosignature as these gases rapidly react with and destroy each other. Their persistent coexistence suggests a constant planetary scale source, replenishing them, a source that could very well be living organisms, but scientists are cautious. They are also looking for technosignatures, signs of advanced technology, and are developing a more sophisticated understanding of false positives, geological or chemical processes that could mimic the signs of life. For instance, a planet with widespread volcanic activity could have an atmosphere rich in certain gases that might be mistaken for biological products. The key will be to build a holistic picture of each world, considering its context, its star's activity, its position in the habitable zone, its geological history, and the full suite of gases in its air. Finding a single gas like oxygen would be exciting, but discovering a complex atmospheric cocktail that is wildly out of chemical equilibrium, with no plausible non-biological explanation, would be the kind of discovery that reshapes humanity's place in the universe. Beyond the search for life, these new instruments will unravel countless other cosmic mysteries. They will probe the formation of planetary systems in their infancy, observing the swirling disks of dust and gas around young stars to watch planets coalesce in real time. They will study the weather patterns on gas giants, mapping the heat and cloud composition of these titans to understand their ferocious jet streams and colossal storms. They will analyze the surfaces of lava worlds and ice giants, providing our first real geological maps of planets outside our solar system. The data they gather will feed back into our models of planetary formation and evolution, helping us understand why our own solar system looks the way it does and whether its architecture is common or rare. This is not merely an incremental step forward, it is a fundamental shift in our relationship with the cosmos. We are moving from being distant observers to becoming active explorers of new worlds, equipped with tools that can sense their most intimate details across the vast gulf of interstellar space. The strange planets we have catalogued so far are merely the opening chapter in a story that is about to become infinitely richer, more complex, and more wondrous as we finally learn to read the stories written in their light. And so our voyage across the cosmos draws to a close, leaving us not with a simple list of facts, but with a profound sense of awe at the sheer, unbridled creativity of the universe. From the supersonic glass storms of HD 189,733b to the incandescent diamond heart of 55 Cancri E, from the eternal, frozen night of rogue planets to the scorching, vaporized rock of Co-Rho T7b, we have witnessed a gallery of worlds that defy our most fundamental expectations. These are not just distant points of light. They are dynamic, complex environments where the very laws of physics and chemistry are pushed to their absolute limits, forging landscapes of molten iron, hot ice, and rain of stone. This incredible diversity shatters the old, Earth-centric view of what a planet can be, revealing a cosmos filled not with variations on a single theme, but with an endless symphony of celestial possibilities. This wild diversity does more than just captivate our imagination. It fundamentally reshapes our search for life and our place in the grand cosmic story. The discovery of Hycean worlds like K218b, with their global oceans beneath hydrogen skies, dramatically expands the habitable real estate we consider viable. It tells us that life, if it exists out there, may not be confined to Earth like twins, but could be thriving in the deep, dark oceans of mini-Neptunes or huddled in the twilight bands of tidally locked planets. The chaotic, wobbly orbits of some worlds remind us that a stable, predictable climate like Earth's may be a precious rarity, a delicate balance that allows complex ecosystems to flourish over eons. Each strange planet we uncover is a data point in a grand experiment, helping us understand the rules of planetary formation, the violence of solar system evolution, and the incredible tenacity with which matter can assemble itself into complex and surprising forms. This journey is far from over. In many ways, it has only just begun. The powerful new eyes we are turning to the sky, from the James Webb Space Telescope to the next generation of colossal ground-based observatories, promise to transform these faint, inferred worlds into richly detailed portraits. We will soon move from simply knowing these planets exist to understanding the composition of their atmospheres, the patterns of their weather, and the geology of their surfaces. We are on the cusp of an era where the chemical signature of a potential biosphere on a world light years away could be detected, and discovery that would undoubtedly be one of the most profound in all of human history. The gallery of the bizarre is still being filled, and every new observation has the potential to reveal a world even stranger than the last, challenging our assumptions once more and deepening our appreciation for the magnificent and wonderfully weird universe we are so fortunate to call home. The true wonder of this exploration is that it invites every one of us to be a part of it. You don't need a telescope to feel a sense of cosmic connection. You only need to look up at the night sky and contemplate the possibilities. Each of these strange planets tells a story of cosmic forces, of ancient cataclysms and slow, patient evolution. So we turn the question over to you, our fellow cosmic travelers. Which of these worlds captured your imagination the most? Was it the pitch-black abyss of TRS-2b, the planet darker than coal, the magnificent ringed spectacle of Super Saturn J1407b? Or the tantalizing, ocean-shrouded mystery of the Hycean world K218b? Let us know your favorite in the comments below. We love reading your thoughts and sharing in this sense of wonder. If this journey through the cosmos sparked your curiosity, be sure to subscribe and hit the notification bell, because we have countless more cosmic adventures waiting for you, from the mysteries of black holes to the search for the universe's first stars. Thank you for joining us on this tour of the universe's most bizarre planets. Keep looking up and never stop wondering.